Good morning, class. In the last video, the last topic we have done was current density. And I told you that a very important part is left in the current density. We'll complete today. What was the definition of current density? That was the current flowing through unit cross-sectional area drawn through that point perpendicular to the direction of flow of current. So you see the definition of the current density. Let's understand this. What does it mean that we have to consider the area which is perpendicular to the direction of current? Let's understand this. Suppose current is flowing in a conductor in this way, right? So this is the cross-section area of the conductor, and current will go such like this. This will be direction of current I. We have to take the area vector along the direction of current. That means we want an area here, dA. Now you can see here, the direction of area vector is always normal outward to the plane area, right? Suppose this is the book, okay? So if this is the area, so the area vector will be outward normal. So in this case, it's fine. You can see that I and dA are along each other. So when you solve it, I will be known as integration dI equals to j dot dA, or simply j dot dA. It's fine. Now suppose the cross section of the wire is like this. Right? It is not exactly perpendicular. So if the current is going in this direction, that this is the direction of current I, what will be direction of this area vector? Outward normal, that is this. This will be dA, but as you know that we will consider only the area vector which is along with the current. So if the angle is theta, then here it will be dA cos theta. So we will consider an area like this. So when you write the equation, then dI will be j dot dA, or simply j dA cos theta. So that is the meaning of that definition, right? We always take the area vector along with the direction of current. Okay, so let's see the next topic. The next topic is basically mechanism of flow of charge in metals, right? So mechanism of flow of charge in metals, free electron theory of conduction. Okay, to understand this mechanism, consider the basic structure of atom. You know, the basic structure of atom contains a positive nucleus having orbits around it, in which electrons orbit around the nucleus in a certain configuration. Okay, because the electrons are revolving around the atom, so the required centripetal force is provided by the electromagnetic force acting between the nucleus and the electrons. Usually the atom is neutral because the total magnitude of the negative charge is equals to total magnitude of the positive charge, because the number of electrons is always equal to the number of proton in an neutral atom. All right. Now, as we move away, we know that force of electrical force is basically inversely proportional to r square. We have done this in the first chapter. So as we move away from the nucleus, the attractive force acting between the nucleus and electron decreases. So now the outermost orbit electron, they are very we can say very easy to detach from the atom. If they absorb very small amount of energy from the outer environment, then they detach from the atom and become free. Such electrons which detach from the atom known as free electrons. These electrons are responsible for the conduction of electricity in the materials. Higher the number of electrons, more conductive will be the material. For example, the number density of the metals is about 10 to the power 29 electrons per meter cube. That means in the volume of 1 meter cube, approximately this much free electrons move from one point to another point. If you measure the number density of the, let's say, insulator, it will be very less. It will be approximately equals to 0, right? Because they don't have the free electrons, and that is why they don't conduct electricity. And that of semiconductors, it lies between these conductors and the semiconductors. So when the electron detach from the atom, now this atom become a positive ion, because obviously initially the positive charge and the negative charge on the this atom was equal, but now when the electron detach from the atom, now that atom become positively charged. These positive charge do not move from their point inside the conductor. Why? Because they are connected with the help of very strong interatomic forces. So they are not allowed to move. They are fixed at a point. But the electrons which detach from these atoms are free to move. So they move in random direction like this. They don't have any proper direction of motion. They move like this. There will be no unidirectional motion of the electrons in the conductor when it is not connected to any energy source. These electrons collide with these ions while they move, right? The point is, if they are moving, that means they are moving with some velocity, and the velocity is very high. They move with about 10 to the power 6 meter per second. They are very high velocity. Now from where this is getting this kinetic energy? They absorb the heat from the environment and convert that heat energy into the kinetic energy. So this speed or velocity is also known as the thermal velocity of the electrons. It is very high. But one more thing I again to tell you, that these electrons do not move in certain direction. That is why there is no flow of charge in conductor, because if one electron goes from here to here, then another electron will come from there to this point. So the total charge flow will be 0, instead of they are moving very high velocity. So that's your mechanism of flow of charge in metals, free electron theory of the conduction. This is a very important conceptual topic. Mean free path, relaxation time, and drift velocity of free electrons. They are basically fundamental how the free electrons moves inside the conductor while there is no source of energy and there is source of energy, both the cases. There are so many questions come from this fundamental. So if you understand how the electrons move inside the conductor, even this concept make you understand how the resistance is offered by any material. So let's understand this topic. Consider a conductor also of length L, right? So let's say this is the conductor. This is a cross section area A. Now in conductor there will be so many atoms, and you know that from these atoms some electrons are already detached. So these atoms becomes positive ions. So these are positive ions. I made them very far, but actually practically they are not so far each other. I'm just to make you understand. That's why the diagram will be understanding clearly. That's why the difference between the atoms are more, right? But again I'm saying practically the distance is basically not that much. It is very less. Now in between the free space there are electrons. All right, so you can see them. We have free electrons, and I told you that these free electrons are free to move in throughout the volume of the conductor, and they absorb the energy from the heat of the environment. These electrons move like an electron gas. You know, you have studied in the class 8th. If we consider gas, then the molecule of gas move in random direction, right? First electron moving in and molecule moving in this direction, then they collide with some other molecule, then they return from their path. Similarly, electrons moves inside the conductor like an electron gas. They move in random direction. So suppose this electron is moving here, it is here. They are moving randomly, no particular direction. Like this. Now while they moving, let's consider this electron. This electron is moving in this direction. After covering some distance, obviously it will collide with this ion, and as soon as it collide with this ion, it reverses direction. So after collision, then it moves in this direction. Now this electron collide with this ion, again change the direction, then let's say it move in this direction, again collide with this ion. So electron keep on colliding with these ions and continuously change their velocity. Because they are moving in random direction, so the average thermal velocity of each electron is always 0. Because suppose I am electron and I'm moving toward this direction, then I'm collide with the ion, then I return my direction, and then I'm moving this direction, then again I'm return collide, and then I'm moving in this direction, again collide, then I'm moving this direction, again collide. So the average velocity of the free electron is always 0. So always remember this part. First, the average thermal velocity of free electron is always 0. Now there are some definitions. Mean free path. What is mean free path? Suppose electron started its journey from here, right? It goes like this and collide with this, let's say, ion A. Then after collision, it moves toward this ion and again collide with the ion B. So you can see that it covers some distance between two collisions. And this is nothing but the mean free path. What is mean free path? Mean free path is the average distance covered by the electron between two successive collisions. Okay, what I'm saying? Mean free path is the average distance covered by an electron between two successive collisions. All right. Then relaxation time. Suppose when it moves toward the ion A and as it collides with the ion A, time started. So let's say time was 10 to the time is 0 second here. And after some time again it collide with this ion B. So let's say this is time T2. Find out the time interval between two collision. So relaxation time is nothing but it is the time interval between two successive collisions. What is drift velocity? I'll tell you now. I think you understand this concept. Now, if this conductor is connected across a voltage source, now what will happen? Let's see. Now, this is the same conductor we have taken earlier. Now, you can see that what the difference here is, now it is connected across a battery having voltage V. And the length of conductor is, let's suppose, L. Now, what will happen? As the battery connected to this conductor, all the electrons will experience a repulsive force from this side to this side, from B to A, because you can see that B is connected to the negative terminal. So all of these electrons start moving in a unidirectional way, like this. See, I have not shown the positive ions here. They are still present here, and there are still collisions are going on. But the only difference is, in the previous case, when one electron collide with the other ion, so they reverse their direction. But here this doesn't happen. Suppose again I am electron, I collide with the ion, right? Then what happened? I change my direction, then again start going in the direction of opposite to the field. I do not reverse my path from A to B. I'll still go from the B to A, so that a particular charge will flow in the conductor. What will be the direction of electrical field? It is always from positive to negative charge. So this will be the direction of electrical field, right? Now by connecting the voltage, all of these electrons start moving in a unidirectional way. They acquire a constant velocity in direction from B to A, and that velocity is known as VD, drift velocity. This drift velocity is of the order of 10 to the power minus 5 meter per second. So that means it's very quite small velocity. Now some student ask that, sir, this velocity is the motion of the electron after connecting the voltage is accelerated or not? So let's find it. F equals to ma, right? Or A equals to F upon m. What will be F? F will be E into E upon m, because F is basically QE. Q is E, electron charge, and E is basically electrical field. We know that electrical field is nothing but V upon L. right? So this can be written as A equals to V E upon ml. All right. So this expression saying that electron must move with this acceleration, but this is not the case. Why? Because again, suppose I am electron, I am pushed with the cell or battery, then I am moving in this direction, I am getting some acceleration. As I am accelerating, suddenly I struck with the ion and I loses all of my energy. That means the energy I have gained from this point to this point, I have all the energy lost by colliding this ion. So that's why when electron move from one point to another move, their motion is not accelerated, but their motion is basically uniform velocity motion. And that average velocity of the electrons are known as the drift velocity, which is order of the 10 to the power minus 5 meter per second. Let's quickly find out the value of this drift velocity. We have so many electrons. Let's consider one electron. Then its final velocity v1 will be equals to u1 plus at. Right. So v is the total average velocity of the electron. v1. u1 will be the, before correcting the battery, they were moving with thermal velocity, and the average thermal velocity of electron was 0. So this will be 0 and this will be plus at. Or precisely we'll write here not t, tau. What is tau here? Tau is the relaxation time. So if you find the average velocity of all the electrons, you will get v1 plus v2 plus v3 up to vn divided by n, right, equals to u plus it's 0 plus a tau 1 plus tau 2 plus tau 3 up to tau n divided by n. So the average velocity of electrons will be known as drift velocity Vd equals to a, and the total average time is relaxation time a tau. So this is the expression of drift velocity. A is acceleration and tau is relaxation time, right? And you know the value of A, we have just calculated, that was the E upon m. So that's how the electron moves while the source is connected. We will cover next part in the next video, that is mobility of electron and the relation between the drift velocity and the current. Till then, thank you so much, class.